Welcome back. So we have just had a discussion on the design sizing of the switches for the sample and hold circuitry, and we looked into the non-idealities associated with the switches, namely the charge injection, clock feed through. There are some other issues also related to the noise of the switch, but here, since we're talking about the ADC and the signal is pretty amplified, we may not really consider the noise produced by the channel current over here. So we are ignoring the noise part. So the two critical components that we have discussed is the clock feed through and the channel injection, current charge injection. Along with that, we have also seen the size consideration based on the leakage current and the on resistance. So these four considerations combined together, the leakage current, the on resistance, the charge injection and clock feed through, can give us indications about the sizing. So based on the off resistance, we determine the value of CS, which is required to store the data with a good accuracy. Next, we looked at the on resistance and confirmed that the sizing ratio for the minimum size ratio for the transistor is good enough to meet the minimum possible T on. We said that the T on could have been reduced relatively further as compared to the on duration or the sampling duration, but we chose a value of say few microseconds, which is a much smaller fraction of the total time duration, total sampling duration that we have. And then we also try to look into other non-idealities like the parasitic capacitance resulting in clock feed through and the channel charge injection, which can lead to inaccuracies. And there also we confirm that a large ratio of CS versus the parasitic capacitances of this MOSFET can be helpful in mitigating these non-idealities. So now once we have considered this sample and hold unit, we can go further and look into other fundamental building blocks of our single slope ADC. The other one that we need to check is the reference voltage RAM that we just discussed. And there we can see that one of the easiest way to produce a reference voltage RAM would be to charge a constant capacitor with a current source. And therefore, if you just have a current source along with a switch which can charge a constant capacitor C ref, it can produce a ramp with a constant slope provided this current remain constant. So this is your I charge, and I can call this switch as say S charge. Whenever this S charge is going on, this voltage will be increasing linearly with time. Also, to begin with, I need to discharge this. I need to set this switch to ground, and I can call this S reset. So when the S reset is getting on, this will be discharged to ground, and then this can be applied as a reference to our comparator that we discussed. This is our CS, the sampling capacitor, and we have the switch over here, which is our S sample. And here we need to look at the timing waveform for the S switch and SR. When are we going to need them? So as we discussed earlier, we are going to use a narrow pulse for the sampling as compared to the overall sampling duration. And this is your T sample, and this is your T on. And as soon as the data is sampled at the falling edge of the T on, remember when the T on is getting off, the data becomes stationary or stable at the CS. And I would like to start my conversion or the ADC operation at that point, and therefore it is the right point to put the SCH on. So I would like to put my SCH on at this duration and keep it on throughout the entire TS minus T on. Just before the T on gets activated again, I would like to bring it down. And this is your S charge, and likewise I have the S reset. The S reset can coincide with the T on. So when the T on is on, you can have the S reset turn to 0, so that the reference voltage is anyway set to 0. So that can be just be coincident with the S reset. This is the timing waveform that we expect, that we'll see how to produce using digital logic. So later when we go towards the components, digital components, the counters and the control logic, we can see the mechanisms through which we can generate this using a single global clock. So in general, the entire system you will have just one clock, and using that you may have to generate the appropriate control signals for everything else. So we'll look into that a little later. Right now I'm just saying that the waveforms available. So in the simulations you will be just required to construct these waveforms using ideal switches, the ideal voltage sources, pulse sources with certain T on T off ratio and certain frequencies suitable to get these waveforms. Now here once again we have discussed two critical components, that is the current source and the capacitor over here, whose choice is going to determine my overall charging behavior. And once again we expect this minimum and maximum voltage over Cref to be close to 0 and VDD respectively, because our input voltage is also having corresponding range, and therefore the ICH over here can we can say I is equal to C dV by dt, where you have the delta V, because this is going to be almost a constant slope, and therefore I can just replace this dV by dt by delta V by delta T, and this delta V is going to be VDD, almost in our case 2 volts, and the delta T corresponds to the entire charging duration. If I assume that this is almost same as TS, because I can ignore this T on, I can take the TS as I guess 0.5 millisecond that we use in the beginning. So I can take this as 0.5 millisecond. As a result, I have C times 2 upon 0.5 millisecond coming over here. And once again, I would like my C value over here to be sufficiently larger than the parasitic components, parasitic capacitances of the switches and the amplifier, because remember, parasitic capacitances can change with the voltage. So if the voltage is changing over here, the parasitic values, especially CGD, CGS, they can change as the voltage changes, and as a result the rise will become non-linear with time. I don't want that. So I would like the Cref to be sufficiently large as compared to all the parasitic capacitances coming at this node. And once again, if I look at the comparators in the switches, even if they are having minimum size transistors, at least we will have, say, a few femtofarads or few tens of femtofarads of capacitances coming over here because of the input devices, and therefore to a safe limit I can choose this Cref to be, say, at least 1 picofarad. So let us check whether if I choose the Cref to be 1 picofarad, which is sufficiently higher than all the parasitic capacitances of these inverters, I will be getting I value, which is pretty small. If I look at this, 10 to the power of minus 9, and as a result, the required I value, you can see it's going to be pretty small as per the required conditions over here. And if I look at, say, so in terms of order of magnitude, you are having just 10 to the power of minus 8 coming over here, which is just 0.01 micro ampere. So now producing such small values of I, definitely it is feasible on chip. If I try to see it, it's definitely feasible to produce such low values of I. However, the precision, in order to maintain the precision for such large or low value of I, you'll have to do a lot of you may have to choose appropriate topologies for the current generation source and the current mirror, so that for such low values, say few tens of nanoamperes, the current precision is maintained. And if we want to have better precision and more robustness, we may like to go for relatively larger charge current over here. So a few tens of nanoamperes or 10 nanoampere may not be a good number, because that is going to have a lot of variation over process and temperature. So remember, for this kind of current, the transistors implementing the channel, the ICH, will be operating in subthreshold regime, and with process and temperature there will be a lot of variations, and it will require a lot of calibration so that this is within a given accuracy. So generally, when we use this kind of very subthreshold current sources, there can be some mechanism through which we can calibrate them, and even after the fabrication we can set them close to the desired value. But the control becomes more and more challenging if they are operating in deep subthreshold regime. Therefore, that may mandate a larger value of C over here. So if we want to have 100 nanoampere, so that you have a 0.1 microampere of current, we can see that will require at least, say, 10-20 picofarad of capacitance over here. So if I choose say 2.5 25 picofarad of capacitance, that will lead to around 0.1 microampere of current, which is relatively safer. Up to 100 nanoampere of current, it is relatively safer. Once you go below 100 nanoampere or 0.1 microampere, it becomes more challenging to maintain these currents to a good precision. So I will select C, say 20 picofarad, which can be of course quite area hungry. It will take a lot of area if I have 20 picofarad. Remember, in the front end amplifier, once again we had limited our capacitances to 10 picofarad and lower, but again once again here in the ADC, the robustness requirement, the requirement to keep these current sufficiently robust over process and temperature, we are forced to have a C value which is larger. Of course, another constraint is also coming from the delta T or the sampling frequency. If you are trying to have sampling frequency which is faster, that is also, or if you are going to have the sampling frequency which is smaller, that is also going to require a smaller delta T, because the charging rate is correspondingly smaller. Ultimately you have to have transition from 0 to VDD. So if you are trying to save power, once again you can see that the area is going to increase. So there are always trade-offs, power and area, power and precision, and so on. So if I try to save power by curtailing my signal to further lower frequency, rather than 1 kilohertz, if I try to curtail it to few hundreds of hertz by using a low pass filter, so in that case probably I will be able to use a larger I'll be able to use a larger T over here. I'm sorry. So if I'm trying to use a larger signal frequency, or if I'm trying to use a smaller delta T over here, then of course for a given VDD, the I required also goes up further, and therefore the once again the power consumption in this particular branch is going to go up. But in general, that power consumption in this branch may not be so critical, because we have seen that the power consumption in the front end amplifiers etc. are sufficiently larger, at least few tens of microampere, whereas here you have we are limiting this current, or we are limiting this current to few hundreds of nanoampere or 1 microampere. Therefore that's not an important constraint. However, area definitely is a more serious constraint over here, because capacitor values of larger than 1 picofarad, the area becomes pretty large. For a 180 nanometer CMOS technology, the area density of this capacitor may be just up to say few tens of around 10 femtofarad per micrometer square. So 1 picofarad, that means you are having 100 micrometer square, 10 micro cross 10 micro, and if you are having say such a large value of 20 picofarad, you can assume correspondingly large area. So the C values take a huge amount of area as compared to all of the transistors etc. The area becomes an important constraint. So this is regarding the choice of the ICH and the Cref. This is just one point that we have addressed. Now we also need to look at the choice of the bias current, or rather the ramp current CH, and also the switches over here. Now here of course switches are going to be much less critical, because they are just supposed to discharge the current to ground, and here it is supposed to just pass the current provided by CH to the capacitor, and therefore I can afford to have the switches to have minimum size, and also we need not worry about the voltage drop across the switches. Even if there are minimum size and the R on of the switches is suppose say 10 kilo ohm, as we just discussed. Here we are looking at the current which is maybe a fraction of microampere, 10 to the power of minus 7 or something. As a result, the voltage drop across the switches will be very small, even they are in triode region and fully on. So we are having 10 to the power of 4 times 10 to the power of minus 7, so less than millivolt drop across the switches when they are fully on. So we would not expect significant drop across the switches. As a result, we can use minimum size transistors without worrying about the voltage headroom over here. Likewise, Here of course it is just supposed to discharge this current, so here headroom is not at all important, but here of course we are trying to connect this current source with the help of the switch to this point, and we know that the current sources need certain minimum voltage headroom. However, and therefore the switch should not eat up that headroom. But remember, the digital switches, we are just acting like switches and turning on and off. They can operate in deep triode region when they are on, and their voltage drop is very insignificant as compared to the voltage headroom of the current source. Therefore, we do not worry about the headroom of the switches. Another point regarding the choice of transistors. So here we are trying to discharge the capacitor voltage to ground, and we know that the NMOS is a good candidate for that. So I can just use an NMOS, I don't need a TG over here. Likewise, this current is supposed to charge this voltage to the maximum possible value VDD from 0, and therefore we know that PMOS is a good candidate for this one, because PMOS can easily charge the capacitive node to VDD. So I can use the PMOS comfortably over here without worrying about putting a TG. So we don't need a TG for either of these two transistors. Now let us talk about the ICH that we are trying to implement. And remember, the constraint for ICH is that we try to keep it as constant as possible. Even if this voltage is changing significantly, we should not allow ICH to change significantly. We should keep the ICH versus this Vref almost flat in order to ensure good accuracy. And for that, once again, we would like to use cascode current mirror. And if you use cascode current mirror, remember, for a cascode current mirror, as we have seen earlier in our discussions, the minimum headroom required is 2V overdrive, provided you use the reduced headroom cascode or wide swing cascode that we have discussed in the class. So we can use a reduced headroom cascode that we have discussed in one of our earlier sessions to implement this ICH. And there also we can make sure that the headroom consumed by that transistor is sufficiently small by using appropriate W by L of the transistor. So if you remember the discussion, we can have our reduced swing transistor, this reduced headroom transistor, where you are having IREF injected into the PMOS, and you are having the same IREF injected over here. And with the help of this, you can bias the cascode current source. This becomes my current source, where I am providing the ICH. So you have the, of course, the switch connected over here. So this is your switch, and this is forming the output branch. And here we know that the maximum voltage this can handle is almost going to be 2V overdrive, where V overdrive is VSG minus mod VT of these two transistors. And if you size these transistors large enough, V overdrive can be made sufficiently small, maybe few tens of millivolt. And we can also make sure that the output, the maximum output over here, which is supposed to match to the maximum output available from the amplifier, which is again VDD minus V overdrive of the previous stage. We can make sure that this limit VDD minus 2V overdrive over here, VDD over here is matching with the maximum voltage that I am expecting at the input by appropriately sizing these two transistors by having sufficient W by L, so that the V overdrive is minimized. There are two constraints. I need a minimum L so that the RO is sufficient, so that the slope remains sufficiently flat. If you use very small channel length, despite having cascode, you may not get a very flat curve. Therefore, you need a minimum channel length so that the curve is sufficiently flat. And also you would like to need the like to have the W sufficiently large, so that the overdrive voltage is small, so that I can we can have maximum possible voltages over here without pushing this transistor into triode, and hence without deviating this current from the required ICH. So the L determined by the flatness of the ID-VDS curve, and the W is determined by the overdrive voltage. So first choose the L to get very flat curve for the ID-VDS, or in this case I would say I out IGH versus the Vref. So this should remain as flat as possible. If Vref is reducing, Vref is increasing, we know that VSD will reduce. So because of channel length modulation, you can get some slope. However, you have to keep the channel length sufficiently large so that the slope is minimum, and then at the same time you have to keep the W sufficiently large so that the overdrive voltage is reduced. So now, if now we have discussed the second critical module for the overall design, which is our ramp circuit for charging the capacitor. We looked into the design or choice of the C-ref and the I charge. We look at the trade off that okay, despite numerical value giving us a very small I, we should not go for that and rather choose sufficiently large ICH so that it is robust enough, it is more tolerant towards process and temperature variations. And also we looked into the considerations for the ICH in order to make it sufficiently constant and in order to ensure that the slope is remaining relatively flatter. Now the remaining discussion is on the most critical block, which is namely your comparator, where we are going to look into the comparator design for the overall operation. We are going to look into the design issues associated with single comparator operation, also going to look at the non-idealities associated with the comparator which can hamper your overall operation or at least reduce the accuracy of your digitization, and trying to propose solutions to that. Along with that, we will look at architecture level how to resolve some of the issues or limitations faced by a single comparator by combining multiple of those and meeting the overall specs in terms of input range, because one of the most important design consideration for this ADC is the input range. We need to make full swing at the input. We need to meet the entire rail to rail swing at the input, and for that again we have another constraint coming into picture. So that we will see that gives rise to another difficulty, and in order to meet the input swing, if you are trying to make some architectural modification, trying to add other modules to make the input range large, we will see that other comparator non-idealities like offset and mismatch can create further difficulties, and we may need to address those issues by having appropriate mechanisms to cancel out the non-idealities. So let us look into the comparator design and trying to look into the transistor level implementation, the issues associated with the choice of the topology, the number of stages, the sizing, and along with that the non-idealities like offset. Before we look into the comparator design, it will also be useful to check out the specification of the comparator that we would like to use, so that we can have some idea about the design parameters of the comparator and look at the practical number that we can have for the target comparator. So if I look at the operation once again, I am supposed to have Ts, the sampling duration that I have chosen is around 0.5 millisecond in this example, and as I have said, the comparator is supposed to compare the ramping Vref with the sampled input signal, and there are two important specs for the comparator that we would need is the gain and the bandwidth of the comparator. So for a comparator, we can use the same two-stage amplifier that we have been using for the front-end application as well as for the filter design and so on. However, we need to look into the overall specifications in terms of gain, bandwidth. So let us first talk about the required gain of the comparator that we are going to use. So once again, if I talk about this entire duration where we are first of all dividing the entire signal level into 15 millivolt segments, and then we are trying to map it into this duration of 0.5 millisecond. Remember that the on duration of the comparator, that is as long as the comparator is high, that means you are having the capacitor, the reference capacitor being charged, and the on duration or the high duration of the comparator determines the magnitude of the signal. So if the Vref reaches the input signal quicker, that means of course the input signal is smaller, and vice versa. And of course that also implies that if you are having a smaller input signal, that would imply that the reference signal is reaching the input quicker, and you are having the comparator output going down faster or earlier. Now if I look at the first metric, that is the gain of the comparator. For that we can arrive at the gain in several different ways. If I look at the analogy for the ramping circuit that we are looking at, there the voltage is going to increase at different time steps continuously. Now, how many time steps do we want in this interval, so that we can have the number of quantization levels over here equal to the number of quantization we want in the ADC. So, we know that the ADC quantization we have chosen is say 7-bit, and therefore, we are looking for 127 different levels, and therefore, we are having the overall voltage signal divided into 127 different segments. Therefore, of course, if you have to measure the entire signal in terms of time duration in this entire 0.5 millisecond, I would like to divide this into correspondingly 127 segments. And as a result, if I look at the counter, which is supposed to give me the count of or supposed to give me the magnitude of this duration, and hence the magnitude of the input signal, that is supposed to be driven by certain clock frequency corresponding to this time division. So, here I would like to have my overall signal or overall sampling frequency, which is 2 kilohertz chosen. Corresponding to that, I would like to have the frequency of the clock given by 127 times 2 kilohertz, so close to 250 kilohertz. So, this is going to be my clock frequency, which is required to give me so many different levels in the time domain corresponding to the required number of levels in the amplitude domain. So, approximately I can take it as 25 kilohertz, comfortable number. And now, if I look at the comparator bandwidth and the gain required to satisfy this 25 kilohertz bandwidth for the clock. So, one important factor would be the speed of the comparator, how fast the comparator should operate, and for that we need to look at the behavior of the comparator between the clock pulses at which it is having a transition. So, suppose the comparator is having a transition at this particular positive phase of the clock, and therefore, this would imply that just before this positive edge, the reference signal was equal to V in minus maybe a small value delta, and just after this particular instance, the reference signal has gone up to V in plus delta 1, and provided this delta 1 or delta 2, provided this delta 1 and delta 2 are sufficiently large, that would imply that just at this instance the comparator should start to change its output from VDD to ground, and before the next clock pulse arrives, the comparator should be able to make the entire transition. That means, if I zoom out this region, if I say that this is the clock which is driving the counter. So, before the next clock pulse comes, that means because the count gets incremented by 1, the comparator should be able to change its state. So, from this particular rising edge to the next rising edge, the comparator should be able to change its output state and settle to the low value, and therefore, I would like to make sure that the settling time of the comparator is definitely lower than the period of the clock over here. So, here I would like to make sure that the settling time which is given by the 3 dB cutoff frequency of the comparator or the amplifier which is being used to use as a comparator, I would like the 3 dB cutoff frequency to be sufficiently higher than the clock frequency that we are using over here. Remember, if you are having an open loop amplifier which you are using as a comparator with the transfer function A0 upon 1 plus S upon P, its overall time domain response will be given by the exponential factor e to the power minus t upon tau p, where tau p is 1 upon p, and in order to make that time constant sufficiently smaller than this time period, so that the comparator can respond fast within this one period, I would like to make sure that the pole frequency of the amplifier that we are using is sufficiently higher than this 25 kilohertz. Good margin would be 4x, so we can keep the amplifier bandwidth or target the amplifier bandwidth to be at least 4 times 25 kilohertz. So, let us keep it 100 kilohertz. We can be more aggressive and try even larger values, but for the time being we can stick to say 100 kilohertz. Now, this is the one quantity that is known. Now, the other quantity that also needs to be figured out is the gain of the comparator, and for that, once again, we can look at it from different angles. One of the possibility is to look at the ramping behavior of the Vref and if I look at the different clock pulses, so suppose the clock is going on and this is the nth period of the clock and this is the nth plus 1th period of the clock. So of course at this point the count is going to increment from n to n plus 1, and suppose the Vref is the Vin is approaching the Vref. So this is your Vref which is ramping up, and this is the Vin which is sampled. So the point where Vref equals to Vin is the place where I have to stop the counter. So if the Vref approaches Vin just at the nth count, just before the nth count, the counter may miss this falling edge of the comparator, because at this point ideally the comparator will go down, but of course the comparator has some finite delay, and the control loop which is supposed to set the counter off is also having some finite delay, so it may end up missing this transition. But definitely before the next transition I would like to make sure that the counter is able to the comparator is able to switch completely to ground, and therefore by the time the signal is reaching or being incremented by this delta V, which is given by the step voltage change between this time interval, we would like to make sure that the comparator is completely able to switch from, say, VDD to ground. And if I assume that this delta V is of course corresponding to the interval or the segment that we just figured out. Remember, you have the total number of segments over here, which is n, which is equal to the total number of segments in the amplitude domain. So if I assume that this delta V is the same as whatever delta V we use as a segment over here, which is 15 millivolt, we would say that within this single clock period, the overall increment over here will also be close to delta V, because it is starting from 0 going all the way to VDD. And for this delta V duration, we should make sure that the comparator is transiting from VDD to ground. So to an approximation we can say that if this is the limit, this is the minimum signal for which the comparator is having having a transition from the minimum voltage level, that is 0 going all the way to VDD or vice versa. So this is output swing corresponding to delta V. So to some approximation I can say that the open loop gain of the comparator A0 should be greater than this full swing, which is 0 to VDD divided by delta V. And in this case, if I have VDD which is say 2 volt and delta V say 15 millivolt, we can see the required gain as say 20 upon 15. So basically 4 by 3 times 100. And once again, if I look at the margin, we would like to have the gain say sufficiently large, so that because of process and temperature variations, if the open loop gain is going down, we can have enough margin. So I would like to make the actual open loop gain in the design at least sufficiently larger than this number, so that because of worst case process and temperature variations, if this number goes down as compared to the expected design value, I have enough margin. So rather than 100, I can keep some margin, at least say few hundreds, or at least say we can pick a number, say 400, which is at least 4 times larger than this. So let us choose a gain which is say 400, which is sufficiently larger. If we want to be more aggressive, we can go for even larger gain, at least say 10 power of 3, so that we have a very good margin, and even in the worst case temperature and process variation, we are having enough room over here. Remember the GM RO product of the amplifier, they are very much temperature process dependent, so we would not like this gain to drop below the required value. So let us keep the value 400, and therefore we would have a gain bandwidth product which is going to be 4 mega. So you're having 400 times 10 to the power of 5 over here. So we can see the gain bandwidth product is going to be 40 megahertz for this particular case. So remember, this gain bandwidth product is sufficiently higher as compared to what we used for the front-end amplifier, which was just around 1 gigahertz. So here, of course, the required gain, open loop gain, is lower. We are just having 400, which is much lower than 10 to the power of 4 that we targeted for the front-end amplifier. But the bandwidth required is also relatively higher, just so that it can operate with this high frequency clock, or it can respond faster as compared to this clock. That is giving us the the lower constraint of the frequency. So we have the requirement for the gain and bandwidth for this comparator. Now once we have the specs, we can go ahead and try to look at the transistor level implementation and the associated issues for this comparator. Any question? So let us look at the comparator design which can meet these specs. The gain that we have over here, as we have mentioned, it's not very significant. In the earlier designs you might have seen that few hundreds of gain can be obtained from a single stage, so we may think that okay, a single stage comparator may be able to do it, but let us look at the issues and try to understand why still we may have two stage preferable, just in order to keep the design robust enough.
Sir, if the sampling frequency is 2 kHz, then the bandwidth of the comparator should be 1 megahertz.
250 kilohertz.
That should be 250 kilohertz.
Oh, sorry, 50 kilohertz. Sorry for the error. So here will be bandwidth is going to be 4 times as to 1 megahertz, and that will just push this up. So I'm sorry for that. I will have a 4000 gain. That is because I have chosen the initial frequency to be slightly higher. If you look at the discussions earlier, we had restricted our signal frequency to 100 Hz, but here I have intentionally taken it higher, at 1 kilohertz, just to make sure that the design is a little more aggressive. Neural potentials can have signal content up to kilohertz, so that is relatively upper limit. But still, I have taken that in order to have a more aggressive limit for the A0. That will just push my A0 up. So now it seems, yes, if I stick to the larger bandwidth requirement, say at least 1 kilohertz for the signal, then of course it seems like.
So why gain is increased?
I guess you have the bandwidth 10 power of 3, and you are having the overall. This is 1 mega, and you have the gain which was 400. And that was also because we are having the overall factor that I said is around 100, but I just took the overall voltage, the peak-to-peak voltage that you have 2, and we have seen that the delta V that we are expecting is around 15 millivolt. So as a result, we are having something like 100 times some integer. So we are trying to gain the gain which is sufficiently large. So if I look at the gain, I have taken it as 400. So gain bandwidth product, if I say this is rather than 40, it is 400 megahertz. So I have the gain bandwidth product given by 400 megahertz, which can be definitely challenging enough. So you are having a overall gain bandwidth product which is 400. So I was basically sticking to the earlier bandwidth. So here intentionally I have increased the bandwidth from say hundreds to a kilohertz. So in our earlier discussion, the bandwidth of the signal was maintained within 100, but just to ensure that the higher frequency content are not lost, I have intentionally increased the signal content or the target bandwidth of the system to be at least 1 kilohertz, and that would mandate a larger bandwidth. Now if I had taken a more relaxed stance in terms of say signal bandwidth, that okay, means let the LPF or the low pass filter reject the contents beyond 100 Hz, so that my DSP can do the required computation within 100 Hz of signal and give us the required information. That would have much relaxed content over here. So in that case, the bandwidth would be just 100 kilohertz, and the gain value product would be 40 megahertz. Still relatively relaxed. But now if I'm targeting higher frequency content in the signal also, of course it translates to trade-off over here. We are having a much higher bandwidth requirement and also the open loop gain requirement. So we can see that if you're trying to extract more information from the data and trying to have larger frequency content in the data, you are paying the cost in the analog domain. You are having to put more gain for the comparators and also the digital part, which is the clock and the control unit. They are going to have become more power hungry. So just like in the analog domain, if you are having higher frequency content or allowing till 1 kilohertz, remember there also you may have to use relatively higher chopping frequency, for instance, because you need to shift the frequency further higher as compared to the corner frequency. Corner frequency may be 100 Hz, but now you need to shift the signal frequency sufficiently higher, at least few kilohertz. So that would also of course lead to increasing power in the front end stages. But along with that, if I look at say even the filter stages, where you are having the anti-chop data which has been down converted to the original frequency, and you're targeting say at least say up to kilohertz. So all the stages, including the VGA and the filters, they will have to process that frequency content. So analog power of course goes up. Here if I talk about the ADC, there we are seeing that if you are allowing larger frequency content in the signal, the overall gain requirement and the bandwidth requirement also goes up, and hence we are having more stringent content on the gain bandwidth. Now here if I take up say A0 of 400, there also still we have the same argument holding true. We have almost say single stage which can achieve this gain, but along with that you have the bandwidth requirement for which you may have to restrict your overall RO values, and hence burn sufficiently sufficiently high bias current as well to achieve this kind of bandwidth, and hence the gain bandwidth product of 400 megahertz. So CMOS technology, if I look at the gain bandwidth product, 180 nanometer can achieve gain bandwidth products close to few gigahertz easily, and therefore this is pretty much within limit, but definitely it is on the higher side, and it may mandate larger bias current in the comparator and hence increase your power dissipation on the comparator. So the design of the comparator therefore will become a lot more challenging, and we need to make sure that within a given power budget we are able to ensure the comparator operation. And we will also see that if we look into other non-idealities of the comparator like mismatch and offset, it may further aggravate the requirement of the bandwidth. So that will come to it very soon. Okay, so let us try to look into the comparator design and try to resolve this issue of single stage versus two stage, and see what are the pros and cons of using just single stage to obtain this 400. Along with that, of course, you have a bandwidth requirement which is also sufficiently large. So you're talking about at least a bandwidth which is pretty large, which is close to say 1 gigahertz, and which is also very much achievable, but it is going to burn a good amount of power in the comparator. So the time delay that you're looking at for the comparator in this case will be pretty large. Pretty small. So let us get back to our comparator circuit, where we are going to use our open loop amplifier and remember for the comparator operation, ideally we did not worry about the biasing point of the output voltage over here, and we are for the two-stage op-amp, of course we have certain constraint. If I use this as an op-amp, we need to make sure that this is at a proper bias point, and that in fact makes in the feedback configuration, of course the negative feedback of the amplifier makes sure that this is operating desired bias point. But for open loop conditions, once again we don't have much control over the single ended output. The differential amplifier or fully differential amplifier, we have taken help of the common mode feedback to set the output to that point. Here that is also not feasible because it is a single ended output and we cannot really take a common mode feedback to stabilize this. If we do take a single ended approach and try to figure out something like the single ended version of the common mode feedback circuit, it would require a very large RC time constant for just providing our low pass filter and extracting only the DC component from here. In the differential half, you have the common mode extractor, which is automatically extracting only the common mode DC value or low varying common mode value. But here if I try to extract the DC value just for establishing a bias point, it will require a very large RNC value or filter values to implement such a common mode feedback or a DC feedback. I should not call it a common mode feedback, but a DC feedback to stabilize this to required value. So therefore for single ended version, generally it is not very feasible to obtain a well-defined DC point in the open loop amplifier if you are looking at integrated circuit, because those kind of very large RC values will not be feasible to extract the DC potential and then put a feedback to the amplifier. Therefore for integrated circuit we don't have a well-defined DC point over here. But for comparator operation we do not worry about the exact DC point because it can go all the way to VDD and ground in normal operation. Remember, however, in order to obtain the frequency response when you're trying to judge your amplifier for meeting the required gain bandwidth constraint, you need to use the appropriate DC bias point so that you can take the frequency response. Frequency response, remember, it is a linear analysis where the simulator uses linear model, the small signal model of the amplifier. And the small signal model needs that the amplifier, the transistors are in saturation. Therefore, in order to use the frequency response, you must make sure that you are applying a proper DC bias over here, maybe VDD by 2, and make sure that this is also having an appropriate DC bias. If you are using ideal values and not having a very drastically different lambda and lambda p, this will not necessarily be in triode region when you are applying VDD by 2 over here. It will be somewhere close, somewhere between 0 and ground, VDD and ground. But only thing you need to make sure is that it is not going too low or too high when you are applying a common potential over here for the AC. So for AC response, you will connect a DC potential over here, maybe another DC potential here, along with an AC potential over here, and sweep and do the AC analysis for the output node. But while doing this, you should just make sure that the DC point over here is not too low or too high, so that these transistors are entering into triode. One of these are entering into triode. For that, you can tweak the bias voltage over here a little bit, so that this potential is not going too down or too up. So of course we know that these are obtained using current sources, and we can in general bias both these using a single current source. But just to take care of the DC bias when you're checking the frequency response, if you use same bias over here and the output of the PMOS is also being just dictated by the DC point over here, it is not necessary that you will have this close to VDD by 2. It may be low and high and pushing this one of these two transistors in triode region also. So just to make sure that it is not happening, you may be able to disconnect this and put a different DC source here at the gate of this NMOS, so that by tuning that you can tune the DC potential, and then you can take the frequency response, because we are expecting that the GM and RO values will not change drastically if the currents are similar. So make sure that you are not drastically changing the currents, but by little bit tuning of the gate voltage, you can just make sure that this is not going too low or too high. So that is one approach, just for analysis sake, when you're trying to do the frequency response and trying to check the open loop behavior of this circuit. Now, once we have the frequency response here, of course, as we said, if we look at the required gain and bandwidth, you have an overall gain requirement which we just estimated few hundred, so around 400, and if we look at the overall bandwidth, which is coming around at least say a few hundreds of kilohertz to 1 gigahertz, so the gain and product is pretty large, and from there we can look at the overall sizing of these transistors and also the choice of the stages, whether we are going for single stage or two stage. Now, if the gain bandwidth product is too large, we know that ultimately bandwidth will be determined by the small signal resistances and capacitances at the output nodes. This is the high frequency node, which is going to give you a critical pole. Another one over here, which is going to give you a critical pole. This is a relatively low impedance node that does not give you a significant. The pole over here is at much higher frequency. So these are the critical poles. Now, if I look at the output node and assume, of course, that you have load capacitance over here which is sufficiently larger than parasitic capacitances, then the analysis will be simpler. In that case, I have the CL times the RO over here determining the overall bandwidth. However, if the parasitic capacitance over here is too small, in that case, if the load capacitance over here is too small, in that case this node may end up dominating. So we can consider both cases. For the time being, we can start with a CL of a nominal value and assume this to be the dominant pole and try to look at the calculation of the W by L values. So we can take 2 minutes break. After that we will resume the discussion.